Good morning, distinguished teacher. This is the presentation for assignment 2. I'm Yang Qixuan, CST2509052. Today I will start our presentation with my teammate Xinren Yuan. Okay, let's focus on the task 1 first. Task 1 is double linked list. And the first part is node structure. This is the foundation of our whole code. It structures the double linked list, and according to the concept of double linked, it contains the data and two separate pointers. We write in the data here to ensure the data type it is integer, and then we struct two pointer, which means that prep points to the previous node and next points to the following node. Together all makes it a double linked list. Then it is its empty function. This is also very important because it checks if the list is empty. It accepts the head pointer as an argument. If the head equals to null, it returns 1, which in Boolean language means it is true. Else it returns 0, which means we can start the following part. And the next function is the insert node allocation. We can notice that this is a double pointer because this function is just not only reads the list, it changes the element in the list. It helps us to add one new element into the list. First, we need to calculate the size of the node, which to make some space for the function to add an element. And also we need to check if the node is null. If it is null, it means the data is not available. Then we return allocation field to remind the user that the data is not available. And the next part of this function is pointer linking because we add a new element into the list, and so the new element becomes the head of the new list. So the previous one element of this new element is null, and the next element of this new head is the old head. If the old head is not null, we use its equivalent to link the new element into the new old head. So it became an ordered new list. And finally, we update the head pointer to the new element. The next function is find node function. And we can notice that this is only a single pointer because we only read the element from the list and not change any of it. First, we use a temp pointer set to the head, and we need to check whether the list is empty. If this is empty list, it is needless to search for the value in the list, and we initialize the position is 1. And then we use a while loop to compare every element from the list to the given value until we find one specific data equals to the given value, so the value found at position, and end the function. If we compare every element from the list and we cannot find any of it equals to the given value, so the same pointer, which means the pointer became null, so it means that the value not found in the list. And our next function is display list function. Also, we need to check if this is empty list as a first. Use the isEmpty function we generate as a first part of the code. Then we also use a temp pointer to set to the head and a while loop. So the temp pointer can combine with any element of the list to present it in the correct order. until the next part of the temp pointer is null. So we present this to end the display list. Also, our final function, also the hardest one, is the delete node function. And there is two parts of the delete node function. The first one is locating. After we check whether the linked list is empty, we use a temp pointer set to the head and locate the target node with a while loop. This needs to satisfy the two conditions, that is, the temp, neither the temp pointer equals null nor the temp pointer, nor the data of the temp pointer equals to the value. We change the temp pointer to the next one until we find the right value to delete. Also, there is also one edge cases, that is a node not found. Represent the node with value is not found if the temp became null, and it displays the whole list. And the next part of this function is the unlinking. If the node isn't in the head, we bypass it by pointing the previous nodes next to the following node. Use this if condition. And if it is the head, we shift the head pointer forward. And we do the reverse for the next pointer, and use this if condition. Finally, we free the temp to free memory and delete the node. And this is the correct output. This is the correct output after we delete the node. And the final part of the task 1 presentation is handles 3 edge cases, that is empty list, single node list, and invalid search value. This can be seen in the sample output. Let me show you. And we put 3 integers into the code, and first search 10 and search 20, for example. And we delete 30, 45. This is the edge cases because we cannot find 45 into the list, and the correct output is the value 35 is not found. And then we delete 10 and delete, let's see, 20. This is the edge cases for the single linked list. Let's see what will happen. Okay, we delete the node with the value 20 and the linked list is empty. This is the correct output. And then we search the list, and this is another edge cases for the empty list. We search 10, but this is already an empty list. We cannot search anything. Let's see what will happen. All linked list is empty. So this is a solution for all edge cases, and that's all for my presentation for task 1. Thank you for your time and attention.
Hello everyone, my name is Xingren Yuan and my student ID is CST108. Today I will be presenting task 2, which focuses on implementing a stack using a singly linked list in C program. First, you might wonder, why do we use a linked list for a stack instead of a normal array? Well, an array has a fixed size. If we use the array, the stack might get full and we can't add more data. However, a linked list is dynamic. It can grow and shrink automatically as we add or remove data. This means there are no strict size limits, which help us save memory and prevent stack overflow errors. And now let's look at how the stack is structured. In the stack, we follow the LIFO rule, which means last in, first out. To manage this, we use a global printer called head. In our code, this head printer acts as the top of the stack. When the program starts, head is set to null, meaning the stack is completely empty. Every time we push or pop an item, this head pointer is updated to point to the newest node. Let's move to the main function of my code. For the push operation, I created add function. It uses malloc to create a new node. Then it puts a value inside. Uh, Links this new node to the current head, and finally makes it to new node. And finally makes this new node the new head. And for the pop operation, I use the withdraw function. This function takes a value from the current head, moves the head pointer to the next node in line, and very importantly, uses a free function to delete the old node and clear the memory. I also wrote display and counting functions. Both of these use a temporary pointer to travel through the linked list from top or bottom. From top to bottom, either printing the values of counting or counting how many nodes there are. And a very important part of the stack is handling errors like stack overflow, stack underflow. Underflow happens if a user tries to withdraw an item when the stack is already empty. If we don't handle this, the program will crash. In my code, before the withdraw function is called, I use an if statement to check if head is null. If it is null, the program prints a warning message and safely stops the withdraw action, like the PowerPoint shows. And to make the program interactive, I designed a simple manual using a while loop and a switch case statement. The while loop keeps running until the user types 4 to exit. Inside the loop, the switch case reads the user's choice to add, withdraw, or count. I also added some input validation. If the user accidentally types a letter instead of a number, the program clears input buffer so it doesn't get stuck in an endless loop. Finally, when the user chooses to exit, the program safely frees all the remaining memory before closing. To give an example of the program's behavior, if I select option 1 and add the number 10, just like the PowerPoint shows the first picture, and then I add 20, the display function will show 20, 10, because 20 was the last one in, so it sits at the top. Next, if I select option 2 to withdraw, just like the middle picture, if I select option 2 to withdraw, the program will remove the and print the number 20, leaving only 10 in the stack. And just like the right picture shows, finally, if I choose option 3 to count, the program will output that there is exactly one item in stack. And finally, in conclusion, I think this assignment helped me deeply understand dynamic memory allocation in C program and how printer manipulation works in data structures. It was challenging to manage the printers at first, but writing the code step by step made it clear. And thank you very much for the listening.
To conclude, I would briefly summarize our learnings and the challenges we faced. Before assignment, pinches and memories seemed very difficult to us. We feel very confusing. But by building the linked list and stack, we finally understood how to use malloc to create nodes and use free prevent memory leaks. Of course, we have some bugs. We had some bugs, and the biggest challenges for your those program crashes, like when we try to restore an item which is empty. To fix this, we learned to handle edge cases. We added simple if conditions to check if the stack is empty before doing any action. We also printed one step. We also printed out step-by-step message to find well the code broke. Solving these problems really improved our coding logic. That brings us to the end of the presentation. Thank you for watching.